Hello, this is Adipai from Multivariable Calculus in Mr. Butler's class, and I'm here to give you a brief lesson on Lagrange multipliers. It's a brief overview of what it's like, what it basically is, what you can do with it, and how the method is done. So without further ado, let's get started. So Lagrange multipliers are used to essentially figure out maxes and mins for certain functions, like multivariable functions especially. It's the easiest way to do that, and it's a pretty easy combination of things we learned in the past that kind of just all come together to make this one idea, this one method that works pretty well. And it's kind of ingenious to figuring out a lot of different, like mins and maxes. So it's a pretty good way to solve those problems. So this could be for like maximizing volume, minimizing like the cost of something, stuff like that. It's really good for like things like that. So you've probably done by this point maybe a LaTeX project on Lagrange, maybe a couple problems about it, you learn about it in class maybe, but yeah, Lagrange is pretty good. It's a pretty good way to estimate things and kind of maximize or minimize things, and it's a good system that kind of works out for those sorts of problems. So the start of where this all kind of really works out is Lagrange's theorem, and that theorem is essentially this. So let's think about your two functions. One is f of x, y, and one is g of x, y. Two multivariable functions, and they're essentially both independent of each other, just two random functions that you can choose. They could be basically anything. So we're going to say f is this function that we use for modeling maybe, I don't know, like volume or something. Maybe it could be like cost, volume, one of those things. Like this is a function for the thing you're trying to minimize or maximize, right? We're going to call that f of x. And then you also have a constraint. This constraint could be like the cost of your box has to be $100 or less, or maybe the volume of the box has to be equal to or less than 80 cubic centimeters or something. That will be this thing, g of x. So this is going to be just a function, and this is going to be a constraint. And what Lagrange's theorem says is that if these two things are the function and the constraint, then if you take the gradient vector of f at some point, x naught, y naught, that is equal to some constant lambda times the gradient of g of x naught, y naught. And lambda, where lambda is a real number. So this looks a bit abstract at first, and it really seems kind of like, sure, maybe that's true, but what's the point of it? Like, what does that actually get you? Well, you'll see. This is going to be the fundamental like sort of basis for the the method of Lagrange multipliers. And what that method essentially says is this. So you're going to have a couple things. You're going to have your function f of xy, and then that g of xy is going to equal, the constraint is going to equal some number, some constant c. So for every Lagrange multiplier problem, you're going to start off with this setup. It's going to be f of xy and g of xy equals c. And with these two things, you're going to set up a couple equations. So you're going to take the gradient vector of this, you're going to get gradient f of xy, and also the gradient vector of g of xy, or gradient function of g of xy. Vector, great, same thing. When you get that, you can set up a couple systems. So you're going to essentially use these two things to solve for the following equations. You're going to get a f, if the gradient vectors are, if this is true, right? So we set up here that the gradient of f times lambda equals lambda times the gradient of g. If that's true, then we can set up the following system. The x partial of f of x, y is equal to some constant, that same constant lambda times the x partial of g of xy. And essentially that's because if this and this are equal, then there's no way that this cannot be true. Like that statement implies that this implies that must be true. So now that we have that, we can essentially do the same thing for the other variables. So we already have x. Now let's make one for y. We'll do f of y, xy equals lambda times, that's like an x. Let me redraw that real quick. Lambda times g of y, x, y. Okay, so now we have our two partials, but then we also, in this system, have this equation from before. So we're going to rewrite that again, and we'll do it in green maybe. We'll just make it different. G of x, y equals c. Okay, so now you set up a system of three variables. You have the variables lambda. Let me change colors again. You have the variables as follows. We have lambda, you have x, and you have y. So you have three variables, and as we learned in Algebra 2 or someplace, we know that every system of three variables needs three equations to be solved. And if you look at that, you have 1, 2, 3 equations. Perfect. So now you have three variables and three equations, and you can solve for each of these terms using that system. So that's, in theory, how Lagrange is done. But to really understand how it works, we should do a practice problem to kind of explain why that's the case. So we're going to do it with one constraint first, because so lambda is our constraint, basically. So we're going to start off with just one constraint. So just three variables in three equations, and we're going to do that as follows. Let's go back to the black marker. All right, so let's say we need to find let's do the fancy way, the example. Let's say we need to find the maximum value of some function f of xy, sorry. And we'll say that's equal to, how about, let's do 4xy. And to make things easier, so if we we're just gonna add a constraint here that doesn't really make, it's not g of x, but it's going to be x is greater than 0 and y is greater than 0. And this is just because if we don't do this one part, we are probably going to get negative numbers as an option for x and y. And while that is usually considered as a point in Lagrange multipliers, for the sake of this first problem, we're going to just ignore that, and we're going to make it so that you only get one possible. You'll see what I mean. But this just makes it a bit easier to define our actual max. So we're going to add our constraint function next. So we're going to say this is our maximum value, and then we're going to start to see subject to the constraint. And for the constraint, let's do x squared over 9 plus y squared for 16 equals to 1. Let's make that a bit more proper. There we go. So x squared over 9 plus y squared over 16 equals to 1. That is going to be our other function. Okay, so now we have our f of x, and then this is going to be our g of x, which is our constraint. All right, so now we can figure out the actual system. So we're going to set that up again and just put it in the general form to make sure we know what we're doing. So let's remind ourselves what we had before. Fx partial equals, what was it, lambda? Almost forgot, g of x. And we also have fy equals lambda gy. And then lastly, g equals c. All right, so we have here our three general form equations, and now we can use these and apply our functions from earlier to actually get real values. Okay, so first we need to find this x partial. So here's a function. We have 4xy. We've all done partials before, so I'm going to skip the explanation. We're just going to go right to the partial. It's going to be 4y, and that equals, lambda is still lambda, that doesn't change. Lambda times the g partial with respect to x, and that's just going to be 2x over 9. As follows. All right. And then we're going to get our next equation. We're going to have the y partial, which is going to be, looking at this function up here, 4x equals to lambda, still unchanged, times the y partial of g of x is going to be y over 8. All right. And then we have those two, and then the last thing is going to be the g of x part. So then we just have, we write down a function again, x squared over 9 plus, that's not really a 9, let me fix that. For 9, much better, plus y squared over 16 equals to 1. Okay, so we now have our three equations. We have x, y, and lambda as our unknown variables, and now we can kind of just solve it. We can just go for it. Okay, so from the first equation, we can kind of get lambda in terms of x and y, and we can do that for both these equations. So we can kind of use these to figure out what lambda could actually be. So the way we're going to do this, we're going to find out what lambda equals and set those to equal to each other. So in this one, we get lambda equals to 36y, wait, let me make sure I get this right, 36y over 2x. Is that right? Yeah, okay, 36y over 2x. And that also equals, if we simplify that, we get 18y over x. Okay, next one. Lambda here equals to 32x over y. And that's already simplified. So if these both are lambda, then we can make them equal to each other. So we're going to get the equation 18y over x, so 32x over y. All right, so now we're going to solve for y and x in terms of each other using this system. So we're going to get 18y squared equals to 32x squared. And then based on that, we can figure out what x and y are equal to. So if we simplify this out, we're going to get, what would it be? 9y squared equals to 16x squared. Or x squared equals to, if we simplify it this way, 9 over 16y squared. Man, these are really out of order. Give me 1 second. Let me just make it a bit more orderly for you guys. Let's move this here. And move this guy over here. Okay, so now we have x and y in terms of each other. So we're just going to simplify this one step further. Get my pen again real quick. X equals to 3/4 y. And you might ask, why am I not doing plus or minus? Well, we established before over here that x and y must be greater than 0. So if that's the case, we can just leave this in terms of the positive and ignore the negative. And if that was not the case, we'd have to consider the negative values as well. But just for the sake of the problem, to be able to simplify your first example, we're going to just ignore the negatives and go with only the positive answers. So now we have x in terms of y. So now using this, we can, what can we do? Okay, so we have this equation for x and y. So we're going to plug this back into this guy over here, and we're going to try to solve for y as an actual numerical solution. So x equals to 3/4 y. So if that's the case, we can plug 3/4 y in for the x in the g function. So we're going to do 3/4 y squared over 9 plus y squared over 16. It looks like a 4, doesn't it? Let me fix that one more time. There we go. Y over 9 plus y squared over 16 equals to 1. Okay. Let's work on that a little bit more. We're going to get 9/16 y squared divided by 9 plus y squared over 16. Now this cancels, and then we get 1/16. We'll just get y squared over 16 plus y squared over 16 equals to 1. And if we simplify that out, we get y equals to 4. Or y squared equals to, wait, sorry, hang on. Let me fix that. That's not right. We're going to get 1/8 y squared equals to 1, which means y equals to rad 8. Sorry about that, guys. It's been a long weekend. Y equals rad 8. Okay, so now we know that y is rad 8, and we know that we can use this to solve for x as well. So if y is rad 8, we can go back to that equation up here, and we can get, let me just copy that for 1 second, just to make things a little bit easier. Copy and paste. Paste. Okay. So here's our constraint, and then now we already have our y value. So we're going to just plug that in as follows. So y equals rad 8, we're going to get x squared over 9 plus y squared is going to be 8 over 16 equals to 1. Okay, so using this, we solve for x. X squared over, that's x squared over 9 equals to 1/2. Multiply by 9, x squared equals to 9 over 2. Take the root of that, x equals to, again, we're going to ignore the negative. We're going to do 3 over rad 2, which is the same as 3 rad 2 over 2, if you want to be, correct about it, I guess. All right, so we have now obtained our value for x over here, and as you can see over here, we've obtained our value for y. So where does this leave us? Well, we now have our solution. So we established that x equals to 3 rad 2 over 2, and y equals to, what was it, rad 8. And this means that our maximum value is going to be at the point 3 rad 2 over 2, comma, rad 8. But the question was, what is that absolute value? So we're going to go back up here, and we see our original function was 4xy. So going back into here, I'm going to write that down again, 4xy. And we're going to just plug in 3 rad 2 over 2 and rad 8 into that function to get our actual solution. So f of 3 rad 2 over 2 rad 8 equals to 4 times 3 rad 2 over 2 times rad 8. All right, let's simplify that further. 4 times 3 over 2 times rad 16, which is equal to 4 times 3 is 12 over 2 times 4. That's just going to be 6 times 4, 24. All right, so that would mean that this Lagrange system that we created up here, this all leads to the answer of 24. Now, while we don't know for sure whether it's a max or a min, there's a pretty easy way to find out. We just plug in a different point. So we know that this thing has to hold true, right? And if we try to think of a point that makes this work, there's a couple that we can use. So x squared over 9 plus y squared over 16, we can plug in any point to that function, and essentially any point you get, we know for a fact is going to be less than 24. If you get a point that's more than 24, then you would know that 24 is not the max, but in fact the min. But because we know for a fact that any point you find for this function, you're going to plug in, that's where x and y are greater than 0, you're always going to get a number less than 24 back in f of xy. So because of that, we're just going to say we confirmed alternate point has value, let's change that a bit, has f value less than 24. That means 24 is our max. Perfect. Okay, so we've kind of gone through this once, and we've discussed how to do the method for one constraint, which is going to be lambda. But there's actually a way to do this for multiple constraints, and while we could go technically like a big number like 7, 8, 9, like 30, we're just going to focus on 2, because realistically that's probably all you're going to need. There's not really many applications where you're going to need to use multiple constraints. So we're going to use it, this is multivariable calc, so we often have functions where it's not f of x, y, but instead f of x, y, z. Now, this is an extra variable, so we're going to already need to consider another constraint that's not just our lambda. So with this, we're going to do things a little bit differently. So for this one, we're going to need a little bit extra. So there's actually 2 constraints, right? So we're going to say that, we're going to use an example from the textbook for this one. So we're going to say that we have, yeah, let's go with this one. So we're going to say, I'm going to write this problem down. So we're going to say let t of x, y, z represent the temperature at each point on a sphere. And we're going to say that t of xy equals to 20 plus 2x plus 2y plus z squared. So as you can see, we have x, y, and z in the same function, so it's going to be a 4-variable problem essentially, because we have this output and then we have x, y, z. All right, so we have that, and then we're going to say that this represents the temperature. I was going to say temp. At each point on a sphere. And we're going to call that sphere x squared plus y squared plus z squared, which is a sphere formula, equals to, let's just say 11. And now we need to find the extreme temperatures on the curve formed by the intersection of the plane x plus y plus z equals to 3. Make that a bit better. And the sphere. That's a lot of writing. Okay. So now we essentially have a similar problem. We're going to try to find extremes of a function, which is going to be our t function. And we're trying to find the only difference is there's not one constraint, but there's two constraints. So it's the intersection of the plane, of this plane, and that sphere back here. So there's two functions that are constraining this. So it's a little bit different from before. And what we're going to do here is we're going to do a very similar thing to the before. We're going to give the first one the name g of x, and we're going to write that down, let's say in blue. G of x, y, and z equals to, here, let me just label this one real quick. Constraint number 1. G of x, y, z equals to, what was it? X squared plus y squared plus c equals 11. Plus z squared, sorry, equals to 11. And then we're going to have a second constraint. We're going to call this one h. Whoops, wrong place. And first, we'll just write constraint number 2 up here. Put it in red. H of x, y, z equals to, let's see, x plus y plus c equals to 3, right? Yeah, 3. Make that z a bit better. X plus y plus z equals to 3. Okay, so we already know that this is something from before. G is something we're used to. We did it up here, but now we also have this other thing, this h, right? So h is a bit different. H is not what we're used to. So we're going to try and make this a little bit differently. So we're going to include things. So the way you kind of include this extra function is as follows. So before we had these general equations. Just to remind you all. We had fx equals to lambda g x, fy equals to lambda g y. Sorry, wait, I wrote these wrong. G y f partial z equals to lambda g partial z. We had these three equations, and we also had g equals to c. Well, here's some good news. This guy does not change. That is the exact same. And these are also still the same, but we add something to them, right? So we had this thing lambda, and lambda is paired with g. So I'm just going to write lambda over here so we remember that lambda, and put it in blue as well, make sure we know. Lambda is going to be the constraint for g. And for h, we're going to use a different constraint. So we already had lambda was taken for this one, and now we're going to add mu. So constraint number 2 is mu. And what this does is it's going to change our general form of equation. So before we had this. The theorem was as follows. Let me use this one again. It was lambda, or sorry, gradient f equals to lambda gradient g. And the next theorem is very, very similar. We're just going to take this, we're going to do plus, and then we're going to add mu lambda, or sorry, gradient h. This is our new theorem for Lagrange. And this is the same thing as before. We're just adding an extra term for the second constraint. So how does this look in practice for general equations? It's very, very similar. So we're just going to literally do plus, and we're going to add a mu term, mu h partial y. And the same thing is going to happen here. Wait, sorry, h partial x. This is y. And then h partial z. And we're also down an equation now because we have 4 variables, we need 5 equations to solve them. And the way we're going to do that is by literally just adding, or sorry, we have 5 variables, so we're going to use 5 equations for this one. We're going to add one thing here, and we're just going to do h equals 2. We'll call it, I don't actually know the official letter for this. We're just going to do C1 here, we're going to do C2 here. Because they're both equal to constants, it's just a different number here, because this one's 11, this one's 3. So yeah, we have our equations here, we have our theorem there. This is going to be how we approach this problem with 2 constraints. So let's see it in practice. We're going to use this problem again. We're going to try and go back to the first one, and I'm going to put that in blue at first. F of x, or we'll do f of x in black. So f partial x is going to be what? Sorry, t. So f of x is going to be. Here, let me write this down just one more time. T is up there. So f is essentially this f function. This function is going to be our t function. So we start off with this t partial x. What is that? So we see an x here. It's going to be 2, and that's it. So it's just 2. 2 equals 2. Let's do the g partial now. So g partial y is just going to be 2y, and it's going to be lambda. So we're going to put that in blue because the g function. We're going to do lambda times 2y plus, and then red is going to be our h function and mu. So we're going to do plus mu times literally just 1. Sweet. So we have our first equation ready. Next, we're going to go to the y partial of f. Of t, my bad. So we're going to do 2 again. That's the same thing. We just take the y partial of this. It's literally just 2. So we're going to do 2 again equals 2. Lambda remains unchanged. And this is just 2y. So it's an x. 2y plus mu times, what is it? 1 again. Last one. So we have a z squared here instead of just a z. So it's going to be 2z equals 2. Lambda remains unchanged. Times, that's probably just going to be 2z. Yep, 2z. 2z plus, and mu is just going to, the mu constant is just going to be mu, and then we have the h partial of with respect to z is just going to be 1. All right, so now we have 3 equations here, and we're just going to copy down our constraints one more time. So the first one is going to be the g constraint. That's just x squared plus y squared plus z squared. Let me make the plus a bit better. That's a very big eraser. X squared plus y squared plus z squared equals to 11. And then lastly, we have our h function, which is just x plus y plus z equals to 3. Lovely. So here we have 5 variables, we have 5 equations, and we're just going to go ahead and solve. All right, so this looks pretty intimidating at first because, you know, we all probably have bad memories of Algebra 2 where we did massive systems and just had a hard time solving them because they just took way too long, but this actually isn't too bad to solve at all. So we're going to look at these 2 things real quick. So if you look here, this actually isn't too bad at all. So we have these 2, if we use a linear combination and we just kind of subtract them from each other, we can get a pretty nice result. So we're going to subtract this minus that, and that essentially gets us the following result. So if we subtract the 2, we're going to get 2 minus 2 is 0 equals to, those 2 don't subtract evenly, so we're just going to do lambda 2x, so it's in brackets, minus lambda 2y. That was a bit better. And then this is just mu minus mu is 0. All right, so if we go to each side, we get, if we add this term to the other side, we're going to get lambda 2y equals to lambda 2x, divide by 2 lambda, y equals to x. Awesome. So we just simplified the equation a bit further, and we have this is just essentially equal to one another. So now we can go back to this and plug in some points. So we have, there's 2 things that actually could happen here. So I made one mistake. So if we look back at this one, there's two things. Either x equals to y or lambda equals to 0. And we don't know which of these is which. So there's essentially two outcomes for each of these, this scenario. There's going to either be this outcome or this outcome. Either y must equal x or lambda must equal 0. So it's easier if lambda equals to 0. We can kind of just grab that and, plug it in. So lambda equaling 0 would be, let's see, 2 equals to, if lambda equals to 0, then we can kind of just go to this first equation once more, and we can go as follows. We're going to grab this, we're just going to point it over there, just to make things a bit easier. And then we're going to write if lambda equals to 0. Then, if lambda equals to 0, then we just get 2 equals to, well, that's just 0, plus mu. So mu equals to 2. And if mu equals to 2, and if lambda equals to 0, then we can go back to another equation and kind of resolve for the other things. So if lambda is 0 and if mu is 2, let's see what else we can do here. All right, we can go and try and solve the last one. So if mu is 2 and we can go to this equation, we can grab that. 2z equals to, well, we know lambda is 0, so it's just 2z equals to 0 plus mu is equal to 2, so it's just that. So 2z equals 2, so z equals to 1. We're getting somewhere, guys. This is progress. All right, so if z equals to 1 and mu equals to 2, then we can go back to, what should we try next? Let's go to this last equation here. So x plus y plus z equals to 3, right? And z equals to 1. So using that equation, let's take this one, pull it out here. X plus y plus z is equal to 1. So we're going to do x plus y plus 1 equals to 3. X plus y equals to 2. Okay, so x plus y equals to 2, z equals to 1. And yeah, we have that system set up. So x plus y is equal to 2 here, and we need, essentially, what we need now is a system to solve for x and y. So we know this, and where can we get our other equation? Well, if we look at this one, it's actually set up in the perfect place for us to, get x and y in terms of each other. So x squared plus y squared plus z squared is equal to 4, because z is 2. Z is 1, it's equal to 1. 1 equals to 11. And simplify that, x squared plus y squared equals to 10. So we have this and we have this. These are going to be our tickets to find x and y. It's a lot of work sometimes, guys, but trust me, it's a good method. So if we're going to use that, we can get x in terms of y. We're going to get x equals to 2 minus y from the first equation. And plug that into the next one, we get 2 minus y squared plus y squared equals to 10. Let's just FOIL that out. 4 minus 4y plus y squared plus y squared equals to 10. So find that out. We're going to get 2y squared minus 4y minus 6 equals to 0. Divided by 2y squared minus 2y minus 3 equals to 0. And that's going to be equal to y minus 1 times y plus 3. Is that right? That is right. Nope, it's not right. Y plus 3. Ugh, my ratio's gone. Y plus 3. Hold on. And that's going to be equal to y plus 1 times y minus 3 equals to 0. So that means y equals to -1 or y equals to positive 3. So we have two possible y solutions. All right, and we're going to plug these back into the other equation, which is x plus y equals to 2. And if y equals to -1, then we know that x must equal to, using this, we can say x must equal to 3. And here, x must equal to -1. Perfect. Let's shrink this down, just erase that plus for the sake of that. Okay. So that means our points must be at one of the following. So we know that z equals to 1 in any case when lambda is equal to 0. So we can essentially use all of this and consolidate it here. We're going to write if lambda equals to 0. Then we have 2 points. Points are either 3, -1, let's see, z was 1, wasn't it? Yeah, 1. 3, -1, 1, or -1, 3, 1. A lot of systems, I know, but we essentially get to these results in the end. We either get the first one or the second one as our actual, solutions. Now, knowing that, we have 2 of our points that could be the thing, and we're also going to show that we have to check the other thing out at, which is the other solution. So we know that when lambda equals to 0, this is the case. So this we can check off. But there still is the y equals x scenario, unfortunately. So here's how that's going to work. We're going to solve the systems again for y equals 0 and x equals to 0. This one I'm going to leave to you guys to try on your own. I'm not going to solve it out on this screen because it is stuff you've already learned. It's quad formula for the most part. It's something you already know how to do, but it's just tedious and takes a lot of time to actually write out. So I'm going to, just for the sake of this video, making it a bit shorter for you guys, just write out the equation that it gets to here to simplify things. So if you solve it out, x equals to y using systems and the quad formula, you'll eventually get to the fact that x equals to y equals to 3 plus or minus 2 times the square root of 3. And given that, you also get that z equals to, I believe it's 3 plus or minus 4 times the root of 3. So now you have a couple points. So you have 4 possible points that you have to test out. Let's see, we have t of 3, -1, 1 from our lambda equals 0 constraint. We have t of -1, 3, 1, also from that same constraint. And then we have t of, 3 plus 2 rad 3, 3 plus 2 rad 3, 3 minus 4 rad 3, and then we have t of, and by the way, this when you solve out the system, you essentially get that if x and y are positive, z must be negative, and if x and y are negative, then z must be positive. So that's why this is negative and those two are positive. That's why this negative sign exists. And if you solve it out, you're going to get that answer as well. So I'll just, again, for the sake of time, I'm going to simplify that here because the video is already pretty long. But yeah, you'd get that negative goes with those two positives, and that positive goes with those two negatives. So that's why you're going to get t of that, and then also t of, if you get 3 minus 2 rad 3, if you do that point, it's going to be 3 plus 4 rad 3 over here. And just trust me on that one. Just take it for granted for now. Okay, so we have 4 points to test out, and we're going to test these out by plugging them into our t function up here. And I have my TI-84 with me, so I'm just going to plug into that, and if you plug those in, you're going to get t of that thing equals to 25, and the same with this one, you're going to get 25 for this as well. This is going to equal to roughly, here, let me get the approximation sign. Roughly 30.3, and this will also be roughly 30.3. Okay, so we have 2 different, and to make them more precise, it's going to be 91/3 for each one, to be exact. All right, so given our 2 scenarios, we've tested every possible extreme of this function with our Lagrange method, and what we've got is when x equals y, we're going to get these results, which is going to be the higher number, which is 30.3, and when lambda equals 0, we get these points, which yield 25. And we found one that's smaller than the other. You can always tell, like, this is clearly smaller than this. So it actually works pretty well because we know which one's the max and which is the min. So t equals to 25 and t equals to 91/3 are our two solutions. And because 25 is less than 91/3, we know for a fact that t equals 25 is the minimum temperature, and t equals to 91/3 is the maximum temperature. All right, so this is essentially the way Lagrange is done for a higher order system where it's going to be two constraints and three variables in the actual function. So I hope that made sense. I know I probably messed up a couple parts there, but as a whole, the answer ends up being correct-ish. So yeah, let's hope that helps a little bit. So I'm going to leave you guys with one problem that you can try on your own, and we're just going to use one out of the textbook. There's a solution on CalcChat if you guys want to check that out. And essentially it's just going to be this. So use, and for reference, is number 47 in the textbook section 13.10. So we're going to say, this is the problem. Use Lagrange multipliers, I'm going to just say LMs, to solve for the dimensions of a cylinder. And to be precise, it's a right circular cylinder, which means that it's your usual cylinder that looks like, you know, that. Well, I don't know what that drawing was. That kind of cylinder, where this is a right angle, and that's your radius. So, right circular cylinder with a volume of some arbitrary V0 cubic units, and a minimum surface area. This is a good problem. I checked this one out for the test, and it was pretty helpful. So yeah, I'd recommend you guys do number 47 in the textbook section 13.10. And the solutions are on CalcChat if you do want to check those out later on. So yeah, this is what I recommend you test out, is to make sure you know this unit pretty well. And yeah, I hope my my lesson was a bit helpful. Hopefully it was, somewhat useful. And yeah, have a nice day.